Hello friends, welcome to my YouTube channel. My name is Nasser and today we're going to talk about cross-site scripting. So I want to start off this video with a bit of a demo of a cross-site scripting bug in eBay that was found back in 2016. So let's look at that. Okay, so let's see what's happening here. So whoever this user is, they have this URL for ebay.com. But look at this little part here about the URL. It contains some kind of a weird value that you don't usually see, and it's JavaScript document.write and then some more string. And look at this, it also contains another URL, but it's not from ebay.com, it's actually an IP address. So let's see what happens here. The user is trying to copy this URL and posts it in the browser and then tries to navigate it. Yeah, so the user has been navigated to this eBay page, which makes pretty much all the sense because it is an eBay link here. So the user tries to use their email or username and password, and they try to sign in. But when they try to sign in, it looks like nothing happens, and they're actually redirected to this URL that was provided above. And when they were redirected there, an iframe was created, and that iframe was loaded in with this URL, which actually belongs to a third-party site denoted by this IP address. And what it's trying to do is it probably grabs the credentials that were submitted by the user, and apparently it was logged or something happened with that. And for the POC here, this person is trying to show this another URL where these credentials are logged. So yep, look at this. This was, so let's just zoom it a bit. And this is the username that this person tried to enter in the login form with this password, and it's been logged here at some other website. So this is a cross-site scripting bug here. If you want to read some more about it, you can just go to this Naked Security link here. I will be posting this link in the description as well if you want to go and look into it a bit. So let's, before we dive in deep into what XSS is, let's see what OWASP tells us about it. So back in 2017, when OWASP Top 10 Web Application Security Risks list came out, injection was at the top of it at A01, and cross-site scripting was at A07. And last year, when they revised this list based on their process, and look at this now. So now cross-site scripting has moved up to A03 as part of injection. And injection has also come down to third rank here. But looks like cross-site scripting became pretty more dangerous than it used to be in 2017. And it's actually a pretty common bug that most applications have. So OWASP tells you that this is something to look out for all the time, and fix it when you find something like that in your application. So what is cross-site scripting? So cross-site scripting is basically a type of an injection attack among so there are a lot of injection type of attacks. SQL injection is one, LDAP injection is one, and cross-site scripting is also one of those attacks, in which some kind of malicious client-side scripts are injected into otherwise trusted websites. And XSS attacks occur when an attacker uses a web application to send malicious code, generally in the form of a browser side script to a different end user. So you can you can probably remember that URL in the eBay video. So that was a URL that had some malicious scripts injected into the URL parameter along with it, and then it can be sent off to a user who would actually end up clicking on that URL thinking that it's actually from eBay. And the end user's browser would have no way to know that the scripts are tampered with and they shouldn't be executed. So these malicious scripts can access your cookies, your session tokens, and otherwise sensitive information that the browser has retained and uses with that site. An example was the credentials that you just used there. So let's see, how does it work? So we need to assume three entities here for this demonstration here. Just a little bit of theoretical demonstration. So there is a malicious attacker, and there is an innocent user, and there is a web server with a website deployed on it. Now, this innocent user here has no idea what cross-site scripting is, and it looks like from what's going to happen here that this web application deployed at this web server, the developers didn't know what cross-site scripting was, and they probably didn't do anything to defend against it. And the malicious attacker here is trying to take advantage of that. So the malicious attacker would actually send the user a URL similar to the URL that was shown in the eBay video. The innocent user takes up that URL from the email or the SMS or whatever other means it had, and tries to open that URL in the browser, thinking that it's something important. And the browser would try to send a request to that site where the URL was pointing to, which was to this web server. The web server would take the request and process it, and without knowing anything about cross-site scripting, would just do what it was told to do, and then send the response back to the user's browser, where the browser would actually interpret and execute the malicious JavaScript that was sent as part of the web page, thinking the code is a legitimate functionality of the website, and thereby trying to access some confidential information that is stored in your browser, or maybe the user had to enter something. And because of that script, it could be taken back to the malicious attacker and giving the attacker access to your confidential information, which nobody really wants to happen. So that's how cross-site scripting works. There are three types of cross-site scripting. The first one and the most easiest and the common variety is reflected cross-site scripting. Then there is stored cross-site scripting, and there is a DOM-based cross-site scripting. So let's dive deep into each of these and look at how it works and how it is exploited. So for reflected cross-site scripting, it's similar to what happened in the eBay video, where a malicious script is provided in the request, and it was subsequently returned in the response when the browser executed the script provided in the response. So let's say we have this URL here, and it has this parameter here called order, which has an integer value. Now, a malicious attacker could use this value and try to inject some kind of script and try to scare you into doing something that you don't want. So let's see how this usually works. They could tamper with this parameter and enter in some malicious script like this. And they could be sending you this URL, and when you actually try to browse this URL in your browser, a request would be sent to the server, and the server would respond with some script and data and an HTML page along with it. And when you execute it, this script here would be executed somewhat like this. Now, technically, if you look at the script, it's not really doing anything malicious, not at the moment. But this could be a tactic that the attackers could employ to scare you into doing something more, such as trying to call the number that's listed down here, so that they could trick you into providing them with your user and passwords or some other information. So there's a bit of a summary here. So reflected cross-site scripting is the simplest variety of cross-site scripting attack, where a query parameter is trusted and not validated by the application server, and it is the value that it contains is sent as is in the response. The browser, trusting the content sent from the server, executes it as is, because the browser doesn't know that this could be tampered with. And the eBay video shown earlier is an example of reflected cross-site scripting. The attackers generally use phishing and smishing and other techniques such as veiling to send you a URL that, and they usually try to make it an urgency in this email or SMS that they're trying to send you. And if you click on this URL, it can allow them to access and exfiltrate any data that you have access to. So let's look at the second type of cross-site scripting, which is stored cross-site scripting. It is also known as persistent cross-site scripting. And we'll just see in a bit why it is called persistent cross-site scripting. So this occurs when the application receives data from an untrusted source and then ends up saving it somewhere without processing it. And when the page is loaded next time, the application just picks up that data and includes that in the response. So let's see this bit of a demo here. So imagine we have this URL that we're trying to access, and it loads up this website or a blog. And some people have put down a comment here, this is a great blog. And we also have this option to add a comment ourselves, which would be subsequently shown here. So I could try to put in something like this and click the submit button to submit it, or I could be a malicious attacker and try to put in a script here, something like this. Now, if you look at the script, what it does is that it actually takes all the inputs on the page, and then it disables all of them and then shows you an alert that your account is hacked. And now I submit this. When I submit it, my comment is submitted and it's saved in the database of the website. Now, elsewhere, when somebody else tries to load the same URL, so let's see what happens. Whoa, what just happened? They just loaded the page, and what happened was what I wanted to happen. The input field was disabled, the submit button was disabled, and I was presented with an alert that my account is hacked. Now again, the malicious user here didn't really try to actually hack the account, just tried to scare you into thinking that your account is hacked and then force you into doing something else. So let's see a bit of a summary here for stored cross-site scripting. In this case, the submitted data was trusted by the website, and the server did not validate it and subsequently saved it into a database. And then when the other person loaded that website, that same data was picked up and sent in the response as is. The browser, trusting the content obviously sent from the server, executed it because it doesn't really know anything about cross-site scripting. And popular example of stored cross-site scripting is MySpace SamiWorm. I'll be sure to include a link to what MySpace SamiWorm is in the description. And I might also create another video describing what this actually is. So tune in for that. So attackers usually submit a malicious script on a website, and then they send you a URL, or you just end up trying to browse that page on that website. It loads the containing malicious script like it happened for the user there. And this could essentially let the attacker access and exfiltrate any data that you have access to and probably don't want anybody to use it. The third type of cross-site scripting is DOM-based cross-site scripting. Now, this usually occurs when the application takes some kind of input from the user and without processing it, uses that data in the client-side JavaScript and then writes it back to the DOM, executing the payload. Now, I don't exactly have a demo here for that, but you'll probably see how this works in our following video. So in this case, the payload is executed by manipulating DOM, which stands for Document Object Model, when viewing the website in the victim's browser. The most common source of DOM XSS is the URL, which is typically accessed with the window.location object. And I have a list of a few common DOM-based cross-site scripting syncs. One of them is document.write and window.location, like we discussed earlier, document.cookie, and eval. Now, eval here is the most dangerous one because eval doesn't really check for anything. It just takes a string that you give to it, and then it executes that script as is without thinking anything or considering anything. So whenever you are using eval, please be very, very careful to make sure that you are not creating a DOM-based cross-site scripting bug in your application. Let's look at the 3 ways that we have for preventing cross-site scripting. The first way is to filter and sanitize all data coming in from the client side. Now, whether it's coming from the previous request or response, or it is provided by the user, it should always be filtered and sanitized. These values and data usually include cookie values, query string parameters, and input data from fields, and also uploaded files if you're trying to parse them and get some kind of value out of it that would be later on used. And the example that we saw earlier for the eBay video and the reflected cross-site scripting, where query string parameters were manipulated, and for the stored cross-site scripting, the input data from the comment field was manipulated. So you need to establish a whitelist where a small set of values are permitted and reject any input not matching that whitelist. And reject all the data and throw an error if the data doesn't meet your expectations and doesn't match that whitelist. For example, the user provided a string where a number was expected. In that case, you need to throw an exception and ask the user to provide a valid numeric value, similar to what we have here. There is a bit of a code check that I've put down here, that if the request parameter is has a numeric value, then it should go ahead. But if it doesn't have a numeric value, then you should throw an exception that. If you go back to the reflected cross-site scripting, remember we had that order parameter, which was supposed to be an integer, but we ended up providing a string in it. Now let's look at the second way to prevent cross-site scripting. You should encode all user controllable data on output. So what this means is, so the browser usually takes 2 kinds of inputs from the response that it is sent. It could be either data or it could be commands. The commands can also be malicious script that may have been added to the response. So if you encode the user controllable data, something from the input fields or the cookie values or some data from the uploaded files, that data is sent to the browser as a data and not a command, even if it is tampered with. And the browser looks at it and sees that it's just an encoded data that I need to show as is and not need to execute any commands that I might see in it. So you should use appropriate encoding for different contexts. Some of the contexts I've listed here are HTML entities. So imagine if you're trying to print something like this in a response, you should always encode this data and then show it like this. So when this encoded form of the data is sent to the browser, let's say in document.write, it would not actually try to execute any of this, but it would just write it on your page as is without trying to execute whatever it wants to execute here. And for JavaScript, if you're trying to output some kind of data in the JavaScript, make sure that you are using encode URI component to encode whatever data is going to be outputted. The attackers can usually, what they can do here is they can escape this data by adding another single quote here and then add some commands here to just continue the JavaScript from there, and the string parameters value there would be just empty, and the rest of the data that was tampered with would just come off as a command that the browser needs to execute. So when you encode this data here, this single code would also be encoded and into something like this, like we have here and here, and the browser would identify it as data and not commands. For URLs, you should also encode any data that is going off as part of the URL. Usually this happens for the GET requests. So the third way and the most difficult way for older applications to implement is content security policy. And you should always implement a restrictive content security policy, because if you don't do that, it's just the same as not implementing content security policy. So let's see. So unsafe inline and unsafe eval are two directives that you should definitely avoid because adding these two directives to your policy would actually prevent it from doing any kind of checks on what response was sent and what JavaScript needs to be executed. So here's an example of a restrictive content security policy. It directs your browser to only use resources from the website itself because of this self directive here, and from example.com domain, except for images, for which we are allowing any kind of source to take up any kind of images and show on your website. I will be making a follow-up video on content security policy to explain all the directives that are available here. But in the meantime, if you are interested in content security policy, you can always Google it and find out how it's implemented and what it actually does to your website. So that's pretty much it for this video. Feel free to post any questions in the comments that you may have. If I missed something, feel free to remind me, and I might follow up it in a different video. And stay tuned for more videos to come. There's also going to be a follow-up video for and how to detect them. We'll be doing some kind of a hands-on exercise in that, so tune in for that video as well. Thank you for watching. Stay tuned.